In this video, we're going to continue our discussion of trigonometry and learn about some trigonometric equations. Now, as you can imagine, a trigonometric equation is an equation that involves trigonometry. But now we're going to be solving for an unknown value, just like we did with algebraic equations. And there's really nothing new to learn in this section, just lots and lots of examples of solving. So let's get right to it. We're going to start right away with the example, solve sine of x equals the square root of 2 minus sine of x. And we're going to solve it first over the interval 0 to 2 pi. Well, to solve this equation, we want to figure out what x is. So the first thing I would do is, well, let me just rewrite my equation. Sine of x equals square root of 2 minus sine of x. And I'm going to group everything with an x on one side. So I'm going to add this side of x to the other side. That gives me 2 sine of x equals square root of 2. And then I can divide both sides of the equation by 2. Sine of x equals the square root of 2 over 2. And so to figure out what x is, I need to know what x values, when I plug them into a sign, will get me an answer of square root of 2 over 2. Well, you should recognize that square root of 2 over 2 is one of our special values on the unit circle. It corresponds to this point here at pi over 4. And since sine is my y values on the unit circle, I know an equivalent y value is over here at this point. And that angle just happens to be 3 pi over 4. So this tells me that I have two answers. X equals pi over 4 and x equals 3 pi over 4. And there's no other answers in the interval 0 to 2 pi because when I go around that circle, those are the only two places where I have that y value, which is my sine value. So there's our answer. But now, what if instead of answering it over just that interval 0 to 2 pi, I wanted every single possible answer? So solve the same equation over the real numbers. Well, I know that I would have x equals pi over 4, but I also know that each time I go around that circle, I'm going to also have the same sign value. So I can add 2 pi, or really any multiple of 2 pi to this answer. One way to write multiples of 2 pi is writing it as 2 times n times pi, where n is an integer. And this is just saying pi over 4 plus all multiples of going around the circle a full time. And then I also have the same thing for 3 pi over 4. All multiples of 2 pi. So when you're solving over all of the reals, you're really just doing the same work you did on the interval 0 to 2 pi. And you just have to add certain multiples of pi depending on when you hit those same values going around the circle more than one time. Let's do another example. So let's solve 1 plus cosine of 3x equals 0. And first, let's just get a general solution, so over the real numbers. Well, I would start the same way I started the last problem. I want to isolate the x, so I would start by subtracting 1. And now I just have to think about what this means. Cosine of something equals -1. Well, if I look at my unit circle, cosine, which is my x value, is equal to -1 way over here at pi. But it's going to equal -1 again every single time I go around the circle and get back to that same point. So I know whatever this input of my cosine is, it's going to have to be equal to pi plus some multiple of 2 pi, going all the way around the circle as many times as we want. And now I can solve this for x by just dividing everything by 3. So I get pi over 3 plus 2n pi over 3. And I should specify where n is an integer. So all of those multiples, whole number multiples. So that's my general solution. X is pi over 3 plus some multiple of 2 pi over 3. Now, if I'm going to solve the same exact equation, but just on the interval 0 to 2 pi, how do we do that? Well, I already have my general solution down here. I can just plug in values for my integers n and make sure they fit in this interval 0 to 2 pi. If I get too big, well, then I throw those values out. So let's just start with n equals 0. If I plug in n equals 0, I have x equals pi over 3, which is in the interval. If I do n equals 1, x is pi over 3 plus 2 pi over 3, which is equal to pi. That is also in my interval. And when n equals 2, x is pi over 3 plus 2 times 2, which is 4 pi over 3, which is 5 pi over 3. And that is also in my interval. But if I try one more, if I try n equals 3, I would have pi over 3 plus 6 pi over 3, which is plus a 2 pi. This is not in my interval. So I know that the only solutions on the interval 0 to 2 pi are going to be pi over 3, pi, and 5 pi over 3. And that's all there is to it. So sometimes it's easier to solve it on 0 to 2 pi first. Other times it's easier to solve it in general first. But either way, you do the same technique and get the right answer. So let's do some more examples solving these trigonometric equations. Really, they just take a lot of practice so that you get comfortable with them, but it's always the same sorts of techniques. This time, let's solve 1 plus 2 cosine of x over 2 equals 0. And we're going to start this by finding a general solution. Well, I'm going to solve it just the same way I solved the other problems. I'm going to try to isolate the x. So I'm going to subtract my 1 and then divide by 2. So I have cosine of something is equal to -1/2. That is a value on our unit circle. Cosine is equal to -1/2 over on this angle here and that angle over there. Now, what are those values? Well, hopefully you have your unit circle memorized at this point, and you're either going to have 2 pi over 3 or 4 pi over 3. So my x over 2 is equal to 2 pi over 3 plus some multiple of 2 pi for going all the way around the circle and back to that point. Or my x over 2 is equal to 4 pi over 3 plus a multiple of 2 pi, going all the way around back to that point. To solve both of these equations, I just have to multiply by 2. So when I multiply by 2, I get that x is either 4 pi over 3 plus 4n pi, or x is 8 pi over 3 plus 4n pi. And that is my general solution to that equation. Now, if I want to solve that same equation on the interval 0 to 2 pi, we're going to do what we did on that last problem. Just plug in different values for n and make sure it fits in the interval. And I'm going to start with this answer for my x. If n is 0 in my first answer, I get x is 4 pi over 3, which is in my interval. And if x is, or if n is equal to 1 on that interval, or sorry, for this answer, I get x is 4 pi over 3 plus 4 pi, but that is too big for my interval. So that's not one of my solutions. Doing the same thing with my other answer, when n is 0, I get x is equal to 8 pi over 3, but that is already not in my interval. It's too big. So I really only have one answer on the interval 0 to 2 pi, and that is x is equal to 4 pi over 3. Well, let's do another one. Solve cotangent of x minus pi over 4 equals -1. And we're going to start with a general solution. So what I have right now, cotangent of x minus pi over 4 equals -1. Let's think about our unit circle and think about where cotangent is going to be equal to -1. That means that my sine and cosine have to have the same value in absolute value, but one of them should be positive and one of them should be negative. Now I have a cosine is negative and sine is positive in the second quadrant, and I have cosine's positive and sine is negative in the fourth quadrant, and it's the point right in the middle for both of them where they're both going to be equal to some form of square root of 2 over 2, and so the ratio will get me a -1. So it's those values right there. So I know the input of my cotangent has to be either equal to 3 pi over 4 plus all the multiples of 2 pi, or it's going to be equal to 7 pi over 4. Plus multiples of 2 pi. And then I can solve both of these equations for x. Add pi over 4 to both sides. The 3 pi over 4 plus another pi over 4 just makes it pi plus 2n pi. Or my x is equal to 7 pi over 4 plus pi over 4 is 8 pi over 4. That's 2 pi plus multiples of 2 pi. Now take a look at what both of these are saying. This is pi plus all multiples of 2n pi. And this one is 2 pi plus our multiples of 2 pi. So this is going to get me all the odd multiples of pi, and this one's getting me all the even multiples of pi. But regardless, I get multiples of pi in general. So x is equal to a multiple of pi. And that summarizes all of the answers in just one nice answer. Now, if I'm going to find an answer to that equation on the interval 0 to 2 pi? Well, the only multiples of pi in that interval are 0 and pi. I'm not including 2 pi because it's not included in my interval. And that's it for that. All right, so we've done some solving with different sorts of trig functions. Now we've done sines and cosines and cotangents. But what happens if we have a more complicated equation than the ones we've been working with? I'm going to do an example next where we actually end up having to factor, even though we're working with trig functions. So let's solve a trig equation that ends up looking like a quadratic equation. Let's solve 2 cosine squared of x minus cosine of x minus 3 equals 0. And we're going to solve it on the interval 0 to 2 pi. So when I look at that equation, it looks sort of quadratic at this point. Remember, quadratic equations are ax squared plus bx plus c equals 0. And this looks very similar because I have something squared, then I have my thing not squared, and then I have a constant equals 0. So to make it a little easier on myself, I'm going to introduce a new variable. I'm going to call it u, and I'm going to say let u equal cosine of x. Then when I rewrite my equation, it's 2u squared minus u minus 3 equals 0. Now, rewriting it like this is optional. It just might make it a little easier for us to factor it. Because now it looks just like a normal quadratic equation that we're used to. So now I can factor. This factors as 2u minus 3 times u plus 1 equals 0. And then I know that either the 2u minus 3 is 0 or the u plus 1 is 0. This first guy gets me u is equal to positive 3 over 2. And the second one gets me u is equal to negative 1. But we are not finished yet. At this point, now we need to plug our cosine x back in because the actual answer to the equation is going to be an x value. So let me take what I got so far. I had u equals 3 halves. So that's cosine x equals 3 halves, or cosine x equals negative 1. Well, this first one, cosine x equals 3 halves, that actually does not make sense because cosine is always going to be between negative 1 and positive 1. 3 halves is 1 1/2. It's too big. So this guy has no solution. But the other one, cosine of x is equal to negative 1, we know that occurs over here at pi. So I would get x equals pi as my solution. It would be pi and then all multiples of 2 pi, but since I'm only working in the interval 0 to 2 pi, that's the only solution in that interval. X equals pi. All right, let's do another one kind of similar to that. Solve 4 cosine squared x minus 3 equals 0 on the interval 0 to 2 pi. I'm going to try to get that x by itself the best that I can. So 4 cosine squared x minus 3 equals 0. I can add 3 to the other side. And then divide by 4. And then I can take a square root. Cosine of x is equal to plus or minus a square root of 3 over square root of 4. Square root of 4 is 2. So I have plus or minus square root of 3 over 2. Well, luckily, square root of 3 over 2 is one of the values we know on our unit circle. So there's my unit circle again. Square root of 3 over 2 for our cosine is this angle here, and also the one flipped over. And negative square root of 3 over 2 is this guy over here and flipped over. So I know this one over here is pi over 6. This is 5 pi over 6, 7 pi over 6, and 11 pi over 6. And those are the answers to that equation. So if you don't believe me yet about how memorizing your unit circle is going to come in handy, hopefully you're going to believe me pretty soon, because as you see, knowing the values of the angles and values of sine and cosine on the unit circle helps us solve all of these equations. It would be much more difficult if we didn't have that memorized. Let's do another one. Solve on the interval 0 to 2 pi. I have cotangent x times cosine squared x equals cotangent x. Now, your first instinct on this might be to divide both sides by cotangent x to cancel out one side, but we can't do that because cotangent of x could possibly be 0, and we don't want to be dividing by 0. So instead, I'm going to move this cotangent x to the other side, and then I can factor. So I can factor out a cotangent of x, leaving cosine squared x minus 1 equals 0. And cosine squared x minus 1, I don't have to do this, but I just want to use one of my trig identities just to show you that they can come in handy. Cosine squared x minus 1 is the same thing as sine squared of x. So now I know that either cotangent x is equal to 0 or sine squared x is equal to 0. Now, my cotangent x is equal to 0 when x is equal to pi over 2 or 3 pi over 2. That's where my sine is equal to 0, but my cosine is equal to 0, but my sine is not 0. Remember, cotangent is cosine over sine, so we need the top to be 0 and the bottom to not be 0 in order to get a cotangent equal to 0. Now for this guy, sine is equal to 0 when x is equal to 0 or pi, but we don't want these actually in our solution. Why not? Well, because remember what the original equation was. My original equation was cotangent x times cosine squared of x equals cotangent of x. But 0 and pi are not in the domain of cotangent, so I can't plug them into my original equation. I end up dividing by 0. So those are not allowed, and that means that my only answers are pi over 2 and 3 pi over 2. So we do have to be careful. It's much easier just working with sines and cosines because they're defined everywhere. But as soon as we start dividing, so on your secants, cosecants, tangents, and cotangents, you need to make sure your solutions actually work in the original and that you're not dividing by 0 when you plug those answers into the original equation. Let's just do a few more examples, just to get a good variety of problems in here. Solve on 0 to 2 pi. And I have cosecant squared of x minus 1 equals cotangent of x. Now, I don't know about you, but I see that cosecant squared of x minus 1, and I think of one of my trig identities right away. It's one of my Pythagorean identities. This left side is equal to cotangent squared of x. Now, again, even though it's tempting to divide both sides by cotangent, we can't do that because cotangent might be 0, and we don't want to be divided by 0. So I'm going to subtract this cotangent to the other side, and then we can factor. So I get cotangent of x times cotangent x minus 1 equals 0. Well, this means that either cotangent of x is equal to 0 or cotangent of x is equal to 1. Let's take a look at our unit circle again. We know the cotangent of x is going to equal 1 when either our sine and cosine are both square root of 2 over 2 or both negative square root of 2 over 2. So that occurs here at pi over 4 and at 5 pi over 4. And then cotangent of x equals 0 when the cosine is 0 and sine is not 0. And cosine 0 here at pi over 2 and at 3 pi over 2. So I get x is pi over 2 and 3 pi over 2. Now let's double check. If I plug any of these values into the original, are we okay? I would be dividing by 0 if my sine is equal to 0 for both this cosecant and for the cotangent, because cosecant's 1 over sine, cotangent's cosine over sine. And my sine is equal to 0 at 0 and at pi. And that's none of the values that I found. So I am okay to have all 4 of these answers as my solutions. So that was an example of where we end up using one of our trig identities and then factoring. Now here's a kind of strange example. Let's solve on 0 to 2 pi. And I have tangent of x plus 1 equals secant of x. And I see that, and it looks kind of like one of our Pythagorean identities, but not anything is squared, and we need to have things squared. So I'm going to be sort of clever, and I'm going to square both sides of the equation, because I know that tangent squared and secant squared are related, so maybe I can get all of the stuff in terms of tangents or all in terms of secants. So let's square both sides of this equation. When I square this left side, I'm going to get tangent squared x plus 2 tangent x plus 1. And then I have secant squared x on the right side. Now that secant squared x I can rewrite in terms of tangent by using one of my Pythagorean identities. Secant squared of x is equal to tangent squared of x plus 1. Now if I move all of this right side over to the left, I'm going to just have 2 tangent x equals 0 left. Divide both sides by 2 and get tangent of x equals 0. Well, tangent of x is equal to 0 when my sine is 0, but my cosine is not 0. That happens at 0 and at pi. But now, since I really did alter this problem a little bit, I squared both sides. We should double check our work to make sure we didn't get an extra answer that actually isn't an answer. That's very similar to an algebra. When we square both sides of an equation in algebra, we often have to check our work to make sure we didn't create an extra solution. So let's check both of these answers. My original equation was tangent x plus 1 equals secant of x. If I check x equals 0, tangent of 0 plus 1, is that equal to secant of 0? Well, tangent of 0 is 0. Secant of 0 is 1 over cosine of 0. Cosine of 0 is 1, so I get 1 equals 1 over 1. That one checks out. Now, if I check this with pi, tangent of pi is 0. Secant of pi is 1 over cosine of pi. Now, cosine of pi is negative 1. And 1 is not equal to 1 over negative 1. So that means my only solution is x equals 0. That x equals pi with an extra solution we created by squaring both sides. So you always should check your work when you square both sides just to make sure you didn't create something extra. All right, let's just do one last example to finish this up. And it's going to be an example where we would actually need to use our calculators to do it, because it's not going to involve values on the unit circle. So let's solve on 0 to 2 pi with exact values for radians, and also solve it with approximations to 1 decimal place in degrees. So we want the answer in radians exactly, and in degrees rounded to 1 decimal place. And our first one is cosine of x equals 0.6. So I would solve this by doing x equals cosine inverse of 0.6 and type that into my calculator to get the degrees. Cosine inverse of 0.6 is my exact value for the radians. But I also have another exact value for the radians. So if cosine is equal to 0.6, that means that cosine is positive, and I'm going to be somewhere over here or down here on my unit circle. So I either have, let's see, if I type it into my calculator, I get x is approximately 53.1 degrees for this first guy. So that would be about this one right here. So my other angle I get by doing 2 pi minus my result from before. So I have cosine inverse of 0.6, or about 53.1 degrees, or I have x is equal to 2 pi minus cosine inverse of 0.6, which is approximately 360 minus 53.1 degrees, which is 306.9 degrees. And that is our other solution. Just one more of these to finish it up. Same instructions, exact values in radians, but 1 decimal point estimations in degrees. We'll solve tangent of x equals -5. I know I'm going to end up muting myself. So I know x is going to be equal to tangent inverse of -5, which is approximately -1.37. So I know I'm down here somewhere in quadrant 4, -1.37 radians. Now, the tangent value is going to be equal over here on this other side as well. Now, my tangent is an odd function. So I know x is equal to negative tangent inverse of 5. And that would get me one of my values. It would get me this guy over here. And the other one would be 2 pi minus tangent inverse of 5. Now, if I type that into my calculator for degrees, I get x is equal to 180 degrees minus tangent inverse of positive 5, which is 101.3 degrees, or 360 minus my tangent inverse 5, which is 281.3 degrees. And I just realized I made a typo here. On this first one, should have pi minus my tangent inverse of 5. That is this angle here, because my tangent inverse of negative 5 was down here, and then I have to use my odd property of tangents and shift my result. So I have pi minus tangent inverse of 5 and 2 pi minus tangent inverse of 5 to get it in the proper places based on my unit circle. And that's all I have for you guys today. If you have any questions, feel free to drop them below. If you're a current student, you can also email or ask in office hours or class. And I will see you guys next time for some applications of our trigonometry problems.